NiCad battery, these are, used to be a little more common, you see them a little bit less now. These are nickel cadmium batteries. And so the anode is cadmium and the cathode is nickel oxide. So the cadmium is oxidized, the nickel oxide is reduced. These are the reactions that are occurring. Yeah, so that's the oxidation of cadmium and the reduction of nickel oxide. So nickel is in a +4 and it goes down to a +2. And so those have about 1.3 volts. And the interesting thing about this, and some of these, including the lead sulfate batteries, you can actually get the reaction to reverse if you put a current across it. The alkaline dry cell batteries, for various reasons, you can't get the reaction to reverse. Different reactions happen backwards. But NiCad batteries, you actually can get the reaction to reverse. If you run it too long, you can actually get other reactions happening in the other direction. So you have to be, make sure your charger is set up to stop it when it's fully charged. Otherwise, they'll just explode. So they're quite light and they're rechargeable, which is nice. You can plug them in, recharge them, and use them. Eventually, after many recharge cycles, you get side reactions that happen at a low rate, but after enough cycles, those side reactions use up all the materials. But you can recharge them by applying a voltage and running the reaction in the opposite direction. So it's functioning both as a voltaic cell and as an electrolytic cell in the opposite direction. So nickel metal hydride battery. Again, the electrolyte here is a concentrated alkaline solution. Anode is interesting. It's a metal alloy, and you use different metal alloys with dissolved hydrogen. So hydrogen can actually dissolve into metals. And then the cathode is nickel coated with nickel oxide, and so the reduction there is nickel oxide going, the same as in the NiCad batteries, nickel oxide going to a lower the nickel going from a +4 to a lower oxidation state. Yes, so the oxidation goes from of an HO in an oxidation state, but it's not H gas, it's the H in a zero oxidation state bound to metal. And yes, you have the metal, the hydrogen dissolved into the metal, not as hydrogen gas, but as reduced hydrogen bound to the metal. And then you get, it goes to water. And that volt, since you can use different metals, the exact cell voltage does change a little bit. And then this reaction is the same as before. Cell voltage, 1.2 to 1.3 volts. You have a range of those. And that really depends on the metal alloy and the concentration of hydrogen in that. These particular ones I've shown are actually 1.2. The book says 1.3. So you can imagine as you vary the metal alloy and the exact concentrations, you'll get slightly different voltages. But they're set up to be used in the same place as NiCad batteries, and so you try to match the voltages so they're about the same, so the devices can run on both of these types of batteries. So you have to set up. This is a case where you can't just make a random battery that's 1.7 volts. I mean, because that's useless. The devices aren't set up, so you have to fine tune them to be sort of the sorts of batteries that are already used. Okay, yeah. So these are rechargeable, long life. More environmentally friendly than NiCad. It turns out that they're greater energy density as well. Okay, so the next battery is actually a little bit different in a really interesting way. That's the lithium-ion battery. And it's different enough from other batteries that actually the research behind it won the 2019 Nobel Prize. And so the electrolyte is concentrated potassium hydroxide solution. That's about the same. The anode is graphite impregnated with lithium ions, lithium +1 ions. So the ions are stuck in between the sheets of graphite. So that is the anode. The cathode is, and so the lithium ions are in lithium plus here. And so the cathode is a lithium transition metal oxide. The lithium is oxidation state 0 here. In its uncharged state, the lithium is in the lithium transition metal oxide. And when you charge it up, then you pull the electrons out and the ions migrate over to the graphite. And then when you discharge it, then the electrons flow back into the cathode and the ions migrate from the graphite back over to the lithium transition metal oxide to join them. And so the electrons for the ions are the ones that are flowing through the battery. And then the ions themselves are the ones that are neutralizing the charge. So you essentially pull the electrons of the lithium apart, and then they come back together. And the coming back together is what drives the charges. So yeah, so you get the reduction of the transition metal in that case, and that's the driving force. And so it works on the lithium ion migration from anode to cathode, causing a corresponding migrations of the electrons from anode to cathode, right? Because they're both moving in the same direction because one is negatively charged and one is positively charged. So it's sort of cool because you're actually getting migration of the same ions that are giving up the energy. And a lot of the energy involved is the ions intercalating in this graphite sheet. So so this is quite different from the others, you know, and noticing the effects that led to this is what really you know, won the Nobel Prize. It's so different, and also because it's so useful. They're rechargeable, they're long life, they're very light, right? Because the electrons are being stored in lithium, right? And almost no metal is lighter than lithium. It is the lightest metal. And so, and you can get a very high energy density. It does mean they're more likely to explode, right? You talk about lithium ion batteries on laptops. So a lot of the work to load up lithium ion batteries is challenging because if you get the high energy density too high, it becomes unstable. A lot of the work is also how can you charge them faster, right? You know, it might take an hour for your laptop is using lithium ion battery. It might take an hour for it to charge. If you charged it any faster, then you get the problem that you start getting instability. So really these only break down when you get like side reactions happening, lithium oxide forming, so you have to be a little careful on the charging because then things can go quite wrong. So these are a little different, but they're super useful right now. Okay. And a lot of variations on these is what is being driven in battery research right now, is how do you improve the lithium ion battery? There's lithium air batteries. Yeah, so there's a lot of research, including in the chemical engineering department, on how to make these better. Okay, so just one, you know, just summarizing some of this. So a lot of the work right now. So rechargeable batteries, the reactions can be reversed by applying a voltage. You just run the same reaction in reverse. You know, the lithium ion one is particularly easy because you don't have to worry so much about side reactions. It's just, you know, pulling the ions out and letting them go back. So overcharge is when you apply a larger voltage than needed to the reverse reaction. And this can be problematic. Sometimes there's no other reactions that occur, so overcharging doesn't really cause any damage. Other times, once you push it too far, there's other reactions that can happen, and then everything breaks down. So, and all reversible batteries eventually fail because no matter what the dominant reaction is, there'll always be some reaction. And these are called parasitic reactions, where you get some of the reactants sort of diverted away into some other thermodynamically stable state, so they no longer participate in it. So of the rechargeable battery types, you can see the energy density, that's watt hours per kilogram. Lithium ion are clearly the winner there by a moderate amount. And if you look at the overcharge tolerance, lithium ion and nickel metal hydride have pretty low overcharge tolerance. You have to be very careful about recharging them, that you don't put too much voltage on or things go down. Lead storage batteries, on the other hand, there's not really any other reactions that can occur, so you can overcharge them fairly much. So if your car, when you're running your car, the alternator is feeding energy back into the batteries, like the batteries just get things started. And so it's okay, if that's mistuned, it doesn't really cause a problem because lead storage batteries with lead sulfuric acid have pretty high overcharge tolerance. So there's one other type of cell we want to cover that's a little different from the other batteries. Rechargeable batteries work by just running the reaction in reverse, applying a voltage and just having the reaction reverse. Fuel cells are a little different, and that is they're batteries in which the reactants, i.e. the fuel, are constantly being added. So even though the reaction goes to completion and you can't run it in reverse, you can keep adding more stuff. So it never runs down, as long as you keep supplying it with fuel. So you can actually sometimes get rechargeable fuel cells that you can charge batteries with by just applying, for example, some ethanol. That's a common fuel cell that's used. So the most straightforward fuel cell is one that uses hydrogen and oxygen. There's safety reasons for that because you don't want to have too much flammable stuff around, but it's the simplest idea. And it's essentially running electrolysis in reverse. So here, the anode and the cathode are both platinum-coated metals. The electrolyte is an alkaline solution. The anode reaction is the oxidation of H2 to water. And the cathode reaction is the reduction of oxygen to OH minus. And so by doing this, you generate electricity and you get water. And that water, you don't run it in reverse. You don't electrolyze the water to get oxygen and hydrogen back. You could, but that would be wasteful because you end up just using energy. The point is to have separate hydrogen and oxygen and supply those and generate electricity. So some other process to create hydrogen or oxygen, or maybe just use it to store the energy in hydrogen or oxygen. And then you put them in the fuel cell and you got electricity as long as you've got a constant supply of hydrogen and oxygen there. And you can do this with other fuels as well. Methanol and ethanol are common fuels to use in fuel cells. And that's the end of this segment.